Okay, I think we're ready to go. Can everyone hear me? You can just wave if you can hear me. Hey, I see a wave. Okay, well, I guess I'm leading this off. I'm Carl Pilcher. I'm the director of the NASA Astrobiology Institute. And I just wanted to welcome all of the students somewhat after the fact to the NAI. I guess these presentations today are going to be all from students sitting around you, Mike, there at Goddard, who have been working with you and others on your team. And I think all of the students know just how good a group of scientists you have to work with. We are really, really pleased to have you in the NAI for the summer. The students and postdocs and graduate students that have been attracted into astrobiology are really just an impressive group of people, and I have no doubt that you are all as well. One of the most exciting things about astrobiology, I think, is the quality of the young researchers and students it attracts in. So I'm looking forward to hearing some of your presentations. Unfortunately, I'm only going to be able to stay for about 20 minutes, and then I have to go off and give a talk to some visiting firemen from Washington, where I spent 18 years before coming out here about a year ago. So I'm looking forward to hearing at least a few of your talks. Hopefully maybe get a chance to meet you all sometime. And I will turn it now over to Mike Mumma.
Well, thanks very much, Carl. It's a really tremendous pleasure to introduce these young people today to other members of the NAI and our associates. We were very fortunate in having 10 exceptional students come to work with us this summer under the internship program of the Goddard Center for Astrobiology. This is our 4th summer doing this. We started the first as a pilot program, and we hope to continue this for many years to come. Without going into any greater depth, we'll introduce each student individually, and then after the presentation of that student's research is complete, we'll ask for any questions from the distributed audience first and also locally. So let me just say that the program today is organized in the context of time, temporal evolution of material from the natal cloud core and the protoplanetary disk on towards analyses of comets and meteorites, then on to evolved bodies, in particular Mars and also the Moon, and finally the horizon of exoplanet research. So there should be something in this seminar today for anyone at any one of the NAI sites tuned in to find of interest. So let's get started. Our first speaker is Ariel Lewis from Eckerd College in Florida, and her mentors here at Goddard this summer were Marla Moore and Reggie Hudson. She's been working in the radiation processing lab in ICES. We'll talk today about carbonic acid and its significance to astrobiology. So Ariel, take it away.
Okay, as Dr. Mumma said, my name's Ariel Lewis. I'm from Eckerd College, and I've been working in the Cosmic Ice Lab for the last 10 weeks. And my project is on carbonic acid. It's a determination of vapor pressure and energy of sublimation and the significance to astrobiology. Some brief background for those of you who don't know: carbonic acid is H2CO3, and you can see the structure right up here. And terrestrially, it's fairly abundant. Anywhere that water and CO2 are at equilibrium, you can find carbonic acid. For example, the oceans, even human blood, and soda pop. But since this is NASA, we are obviously more interested in carbonic acid on the extraterrestrial level. And so one of the ways that carbonic acid is formed is actually by the irradiation of water and carbon dioxide ice. So anywhere that water and carbon dioxide ice can be found, there's the potential for carbonic acid. So anywhere you see on this table that's white is somewhere that both water and carbon dioxide ice have been found, and so holds the potential for carbonic acid. And one of the places that was in white is Callisto, one of the moons of Jupiter. And this in red is one of the spectrum that we took in our lab, and in comparison to spectra taken from a spacecraft. And this 4.25, 4.27 peak is actually carbon dioxide, but this 3.88 peak is still, as of yet, unidentified, and there is the real potential for that to be a carbonic acid peak. Just since it's only a one peak identification, you obviously can't be sure from that. And in the lab, as I said, you can form carbonic acid through irradiation of water and carbon dioxide ice, but you can also form it through acid-base injection, which is the method I used for this experiment. And you take the acid and bases up into this needle, inject them into the spectrometer here, and then you can rotate the cryo head and take a spectra through the window. The reactants that I used for this were hydrobromic acid and potassium bicarbonate in order to make carbonic acid. As you can see, the spectrum down here are significantly different, and the carbonic acid is the telltale sign of the carbonic acid spectra is this 13, 15, 1700 peaks right here. So this is what the raw data looks like. We synthesized the carbonic acid and then heated it up to a specific temperature and let it anneal and took spectra every 12 minutes. And then I'd take the 1300 peak and the 1500 peak and integrate these two peaks and see how they changed over time. And then I'd take those raw band areas, multiply them by 2.303 in order to account for the logarithmic scale, and divide by the A value. And then plot this, which is the column density, versus time, and the slope of those lines is the sublimation flux. Then you could take the sublimation flux, and the sublimation flux is equal to the vapor pressure over 2 pi mkt to the 1/2, where m is the molecular mass, k is the Boltzmann constant, and T is the variable temperature. So you could find the vapor pressure purely from knowing the band areas from the IR spectra. And so after doing it at various temperatures, this is the vapor pressure versus temperature graph that I just determined. From 240 to 255 K, the vapor pressure for carbonic acid was determined to be 1.54 times 10 to the negative 12 times the temperature, so minus 3.67 times 10 to the negative 10. And there was actually enough data to even do a heat of sublimation, which is the natural log of vapor pressure versus 1 over temperature. And the heat of sublimation is equal to the slope of that line times the gas constant R, 8.314 joules per Kelvin mole. And the heat of sublimation for carbonic acid was determined to be 66.3 kilojoules per mole, which is logical considering we have also heats of sublimation for acetic acid and formic acid, which are very similar to carbonic acid, and they're 62 and 68 kilojoules per mole respectively. So in conclusion, carbonic acid is all around us, but it's very hard to isolate. It's very likely present in space, though we haven't found it yet. Vapor pressure can be determined from IR spectra. The vapor pressure of carbonic acid is less than that of water, which is significant because that means that carbonic acid can stay around longer than water and could potentially protect water subsurface on anywhere that carbonic acid is formed. And knowing the vapor pressure of carbonic acid will aid in predicting where the molecule might be found. And I'd like to acknowledge Dr. Moore and Dr. Hudson and Dr. Cooper for working with me in the lab, Steve Brown, Tom Ward, and Eugene Gerashenko, Corey and Evie, and the rest of NASA. Thank you.
How about that?
So I think we'll turn first to our colleagues outside of Goddard at remote sites. If anyone wishes to make a comment or ask a question, please go ahead and do so.
Hey, this is Carl. I just want to say how impressed we all here at NAI Central were with the professionalism of that presentation. Congratulations.
Thank you.
You're here. Okay, anything from Penn State or Carnegie? Anybody else online? If not, we'll go ahead and turn to the comments here in the audience or questions. Anybody here at Goddard want to raise an issue or raise a hand, clap again? I have a question. Does this mean I should never drink carbonated beverages again? No Cokes, no Pepsis?
No, it's fine.
Okay, very good. Well, thanks very much. Let's move on to Steve Manning. Steve is from the University of Maryland, and has been working here this summer with Joe Newth and Natasha Johnson. And he'll describe his research on amorphous iron silicate grains as catalysts for organic synthesis in the solar nebula.
Alright, my name is Steve Manning from the University of Maryland College Park, and this summer I worked on amorphous iron silicate grains as catalysts for organics in the solar nebula. I worked under Dr. Joe Newth. First, some background. Previous research has shown that the solar nebula can act as an organic chemical factory. Interstellar dusts and amorphous iron silicates dominate the solar nebula, and the many active sites on the surface of these dusts allow the abundant gases, hydrogen, nitrogen, and carbon monoxide, to react on the surface. And as more reactions occur, the surface generates an organic residue catalyst, and this is cycled throughout the solar nebula and bring organics and meteorites to areas they may not have been able to form otherwise. And this is a closer look at the synthesis that I will be working with. It's a dust grain catalysis, and you can see in the top three up here that the amorphous iron silicate grains allow the free-flowing gases to react on the surface, and as more and more gases accrete onto the surface, an organic residue forms and more advanced organics develop on the surface. And previous hypotheses were that as these silicate grains get coated, like number 6 here, completely in organics, that they couldn't perform efficient catalysis any longer, and the reactions would effectively stop. But recent research by Newth and Hill has shown that reaction rates are actually maybe increasing as gases are passed over these organic residue catalysts. And so my job this summer was to conduct experiments to determine the catalytic rates of these carbonaceous deposits on the iron silicate and compare them to the rates of the actual iron silicates themselves in a laboratory environment. And it's important to astrobiology because it helps determine rates for forming important and maybe possible prebiotic organics in the solar nebula. And this diagram here is of the setup that I was using. It's a closed system that we would put in 75 torr of carbon monoxide, nitrogen, and 550 torr of hydrogen, close it off, and cycle through with a bellows pump. And as it flowed through the system, it would pass through a heated finger with the iron silicate grains, and reactions would happen, and they would flow through the system to the IR spectrometer, or FTIR spectrometer here. And then every run, after a few days of taking spectra, we would suck out the pressure to 0 and then put in a new group of gases so that we can measure the rates in each turn. And what we found out is that the most significant changes happened in the first 2 hours of the experiment, and as the grains became coated with the residue, carbon monoxide reacted faster to produce more organic products, and they increased in rate and in greater quantities. And you can see here that the blue line represents the first run, and the reactants are taking longer to react, and less of them are reacting than the further along reactions, which they happen faster and more of it gets reacted. And next I did an analysis of the catalytic process, and at the top here is a graph of the product methane, and as you can see again, it groups all of the runs together, and the first one here at the bottom is the first run with just the clean grains, and it's taking longer and making less product than the successive runs once the organic coating has developed. So I picked an arbitrary point on this graph, 1.0 in this case, to figure out the amount of time it took for each run to reach that level, and I came up with graphs like this at the bottom, and it's an approximation of the rates. And looking deeper into that, we found that each of these graphs show two important features, and the first is right here. They all showed an initial drop at the beginning, and that represents quickly changing rates of the iron silicate catalyst being coated. And then about the third or fourth run on, they had a much faster steady rate that represents the catalysis from then on with the organic coating that had developed on the top of the grains. And similar plots we made like this for 300 and 500 degrees Celsius. So with 3 temperatures done with plots like that, we could make an Arrhenius plot and determine relative activation energies for each reactant and product. And we took the natural log of time to reach an arbitrary point on either catalyst, iron silicates in this case, and residues in this case. And the slope of the approximation times the gas constant is the activation energy that we were looking for. And what we found is that in the first two here, two products, CN and CH4, they had a lower activation energy with the residue catalyst than with the original iron silicate catalyst, showing that although these are relative approximations, it still gives a good indication that catalysis was happening faster and is more is a better way to do it, a more favorable reaction once the residues have formed. But with the reactants, it was the opposite, which can be expected because this is carbon monoxide was the first thing we could measure, and they were put onto clean grains, so it was easier to deposit just carbon monoxide on clean grains than to compete with the products that would be in by this stage. And the conclusions we came to were that the iron silicate grains provide an initial catalytic surface for organic compound production from carbon monoxide, nitrogen, and hydrogen, and the carbonaceous coating forms on the silicates after repeated exposure, about the second or third flush of the reactive gases through the system. And the organic coating formed but did not stop the catalysis. The rate was actually even greater than that of the clean silicate grains. And the most important part is at the bottom here, that the catalytic nature of the organic coating allows for further production of important and possible prebiotic organics throughout the solar nebula, even after these silicate grains have become coated, since the coating is actually a better catalyst than the original grains, which was the original hypothesis. And these are some future directions and acknowledgments that we will be working towards from that. Good.
Thanks.
Well, thanks very much, Steve. Let's go first to our remote colleagues. If any questions or comments from online sites, now's the time.
Hi. Can you hear me? Bob Menard at Penn State? Okay. I just wanted to ask him, he reported CN. Is that CN radical that you were detecting or HCN?
The peaks that we were looking at, it was in the original 2002 work with this, it was just a cyanide derivative, or we looked in the area of where CN peaks would be found, and so we didn't have a GCMS or a way to figure out exactly they're in these, so it was just CN organic compounds.
Okay.
How did you measure the CN compounds?
We had an approximate, Dr. Hugh Hill had earlier during these had decided on some peaks that would be good to look at, and one of the areas of the CN peaks he had marked off, and we used that from when he used it in his research, so I could keep it consistent because he decided, they said that would be a good spot to look for.
Anyone else online? Okay, how about around the room? Anybody here at Goddard wish to ask questions or make comments? I just wanted to comment that I think this is very interesting and potentially quite important work because everyone who thinks about coated interstellar grains that fall into the nebula thinks about thick coatings of ices and organics. And what you've shown is that this happens naturally in the laboratory. You don't have to start with a fresh silicate surface each time to keep building it up.
And it's faster once they've been coated.
Yeah, that looks pretty good.
Did you say what iron silicate you were working with?
Amorphous iron silicate smokes made in the lab here.
These are the interstellar analogs that Joe has been
making.
Yeah,
in the Goddard's dust chain area here.
Right.
He's been making.
Yeah. Okay, good. Thanks very much, Steve. Next, we're going to move on to macroscopic bodies, and we're going to begin with Kara Rehan, who is a student at Iona College. She worked here with Mike DeSanti as her mentor, and we'll talk today about the chemical composition of comet Q2 Machholz. So, Kara, take it away.
My name is Kara Rehan, and I work this summer with Dr. Michael DeSanti on the organic composition of comet Q2 Machholz. Comets are thought to have delivered water and the first organics to early Earth during the late heavy bombardment, and by studying them, we can begin to learn the chemical conditions of the protosolar nebula and also what they may have delivered to Earth. Comet Q2 is a long-period Oort cloud comet that was observed on 2 different dates. And comets are formed from multiple icy cometesimals, so by observing them on 2 different dates, we're actually observing the different cometesimals. And this is a test of their hetero or homogeneity. Data are taken at Keck 2 on Mauna Kea, Hawaii, with the NIRSPEC. And NIRSPEC is an shell graining spectrometer that we can place filters perpendicular to the shell grating, and so we can select wavelength regions that we want to focus onto the chip. Now this isn't to scale, and we resolve the coma instead of the nucleus, but data are taken with 4 frames with the comet in 2 positions in an A, B, B, A pattern. And this is for fainter objects. With brighter objects, we nod off the chip. Okay. This is an A frame NIRSPEC oscillogram, and on the left is the wavelength and frequency ranges observed in each order. And the right is are the molecules routinely observed in each of those orders. The importance of NIRSPEC being cross-dispersed is that all of these molecules are observed simultaneously, which decreases the systematic error and also allows us to compare them to water, which is very abundant on comets, and we use it as a baseline. Okay. And by subtracting a B frame from this, we can see a lot more features and contrast. And at the top is, or on all the orders, are the A and the B beams, and those are actually the dust continuum of the comet. The bright lines on the A and B beams are the comet emissions, and since NIRSPEC is ground-based, we also get atmospheric absorptions within the orders. We're going to focus on 23 just to look at it closer, and it's bright, so the comet lines are easy to see. After cleaning and spectrally aligning the data, we get this straightened spectral order, which we can extract a spectrum from. To get rid of the atmospheric absorption lines, we apply a synthetic atmosphere absorptions model and align it with the mean cometary continuum, which is the blue stars, and subtract it out. The residual left is the comet spectrum. And right here you're looking at the R branch of methane. Up here, this is named. And just as comparison to another order in a different filter, and another symmetric hydrocarbon this is the Q branch of ethane right here. And we use fluorescent models to a lot of our data. This is order 16, an M-wide filter with carbon monoxide and water. And in order to study carbon monoxide, we have to get rid of these water contributions behind the CO line, so you can see that they're right here. So we apply a predicted fluorescence emissions model of water to the spectra and subtract that out, so what we're left is just contributions from the CO's emissions. We use the fluorescence model again to derive many of our principal measurements for comets. And since those emission lines are temperature dependent, by finding a best fit fluorescence model that best fits with the predicted data, we can get a rotational temperature. And the ratio of the observed line flux to the predicted model is proportional to the production rate. So we can derive production rates, which is the rate that molecules are released from the nucleus and into the coma. And the mixing ratio is the percent abundance of the production rates relative to water, or of the molecules relative to water. Now this is the results from November of 2004. And each section refers to the different filters, and the water production rates in each of those filters were the values to calculate the mixing ratios in each of their respective filters. This is a little busy, but mainly we focus on the mixing ratios. And this is the November data compared to the January data, the mixing ratios. And you can see that over the results that we have, they agree within 1 sigma. So this implies that Q2's nucleus is homogeneous. Okay. And I'd like to thank Dr. DeSanti and Dr. Bonev and Villanueva for helping me out along that. All the interns. It was great. Thank you.
Okay, thanks very much, Kara. So let's go first to our remote colleagues and call for questions from the remote sites. Okay, how about here at Goddard? Anybody at Goddard wish to make a comment or ask a question? Well, I was kind of curious as to why in January 3 molecules were missing under the comparison.
They're on the back burner, I guess. They're waiting to be...
So you were just showing 2 molecules that have been measured by other people, whereas you had done all the work in November's, as I understand it. Is that?
January was done by Dr. Bonchovanov and Dr. DeSanti also.
Yeah. Okay, thanks very much.
Yeah.
Well, there's a question here. Josh turn.
Just wondering what that Q, you were talking about Q branch of ethane or something like that. What's the Q branch of question?
Oh, he was wondering what the Q branch of ethane was. Molecules, those are row vibrational lines, and molecules that aren't linear have P branches, Q branches, and R branches, and it just refers to, I wish I had a diagram.
There's different branches, different carbon chains.
Yeah, the R and P lines refer to changes in different quantum numbers, and Q branches refer to ones that step up to the same quantum number after the rotation transition, I guess.
So keep that question, and next summer when Kara comes back for a second internship, she'll answer this in great detail. Okay, anyone else? Actually, Kara, the work you have done addresses a fundamental question of cometary science, which is, are they all homogeneous internally, or do some contain cometesimals that are formed in different regions of the protoplanetary disk? So I think this is a very interesting result that you presented. Okay, thanks very much. We're going to move on to meteorites. James Doty, who is currently a student at Rice University and has been working here with Jason Dworkin and Danny Glavin, will discuss a search for purines and pyrimidines in carbonaceous meteorites. And I would comment that both of the next two talks, James and Josh's, were done with the new Astrobiology Analytical Lab that was funded in part through the NAI grant, but also in large part through Goddard cross-sharing. And anyway, take it away, James.
Thank you, Dr. Muma. As you said, my name is Jim Doty. I go to Rice. It's in Houston, Texas. I'm going to be talking to you a little bit about aromatics in carbonaceous meteorites, specifically CM2 type meteorites. All right, here's an overview of the carbon cycle in our universe. And you've heard talks from my colleagues earlier, and the processing that goes along and gets incorporated in the comets, and then eventually some of this material will get delivered to Earth. A good idea of the kind of organics that get delivered through things like Murchison come in meteorites. And so our question is to answer what kind of organics in this lab, and mine is most specifically aromatic compounds, such as purines and pyrimidines. Okay, as far as their importance to astrobiology, purines and pyrimidines are ubiquitous to the life that we have here on Earth. They are incorporated into the informational molecules in life. They're used in catalysis, and also in the origin of life, the RNA and pre-RNA worlds, it is hypothesized that they are crucial for those types of life to get started. So, the traditional protocol for getting these compounds out of meteorites required a long, painful process that involved many solvents and induced contamination, and we would only get about a 45% recovery rate. Daniel Glavin got his PhD developing a sublimation protocol, which is much simpler, takes about a day, and has a much higher average recovery rate. Sublimation is very easy. You take your meteorite extract, you grind it up, and you make formic acid extract. That's basically just making a coffee out of it. You boil it in the formic extract. Place the extract at the bottom of the sublimation tube, evacuate it, and place liquid nitrogen in the cold finger. At reduced pressure and elevated temperature, the compounds of interest, the organic ones, sublime, and the minerals that interfere with our analysis are left behind. This is how we do our analysis. We use a separation using HPLC, which merely separates out compounds based on solubility. We then pass them to two detectors. One is a UV absorbance detector, and the other is a time-of-flight mass spectrometer. The mass spectrometer we use uses a soft ionization technique, that is electrospray ionization, which gives us the mass of the parent ion plus one proton, and this gives us very little fragmentation pattern. So what we get is the molecular formula of our compound, but no structural information. Let's take a moment to familiarize ourselves with what our data looks like. On the bottom trace, we have relative absorbance versus retention time, and then the chromatograms on top are traces of mass. In UV absorbance, each peak corresponds to one specific compound that is eluting off of the column. Above, a mass trace tracks when ions of certain mass are coming to the detector. So in the UV, you can see that some of the compounds overlap, but this ambiguity can be resolved by using their specific mass. Also, at each time, we can see that there is a mass spectrum, and this shows you how you can see the mass of adenine, and then adenine with 1 C13 and with 2 C13s. We ran our analysis with 3 meteorites. Murchison landed in Australia. Lu and ALH both landed in Antarctica. Initially, we identified xanthine, uracil, and guanine in these meteorites. And ALH, is good to note, is depleted in UV-absorbing organics. This corresponds well with a study on the amino acids in ALH as compared to these two. And ALH was depleted in the amino acids. These are all very good comparisons amongst these meteorites because they're all of the same petrological grade. Okay, here's that same plot you saw for the standard, but for Murchison. And while you can see that the compounds for my standard don't appear to be in there, compounds of the same mass, that is the same molecular formula, but different retention time, thus speaking to a difference in chemistry or a difference in the way the atoms are arranged in the molecule, shows us that there are many possible isomers of my standards in this. So the way to go about identifying these is to expand the library. With the help of Dr. Henderson-Cleves at Carnegie and here at Goddard, we were able to amass a larger library of these aromatic compounds. So to go through a little process of how we take these, we're going to pick one group, naphthalines, and focus in on the oxidized naphthalines. If you just put one hydroxy group on, there are 2 isomers. They were predicted to be in carbonaceous chondrites, and they have a positive mass of 145. So you go to the data from the meteorite that we collected and look for mass 145, and there's a promising peak. Then you run the standard, and under the conditions that we ran our standards, and we did not get any ionization. The small peak you see there is actually a C13 peak of another compound. So under the procedures for the extraction of the meteorites, I can say that there's no naphthals present, but maybe under better techniques you might see them. In conclusion, the sublimation improves over the older extraction procedure. We are able to detect biologically relevant nucleobases. The MS trace shows that there's many interesting things that we need to pursue to identify these other compounds. And it is interesting to note that the functionalized aromatics of meteorites are not well studied. So this is important to understand the chemistry of the parent body and what got delivered to Earth for the origin of life. And I will turn it back over to Dr. Moore.
Okay. All right, so that's pretty interesting stuff, and I'm really pleased that you mentioned our collaboration with Carnegie, particularly since Carnegie's online. No, but just teasing. There is a very vigorous collaboration going on between the analytic astrobiology groups at Carnegie and at Goddard. Let me call for questions first from our online colleagues.
Hi, Bob and Art at Penn State again. Did you run a control where you didn't do the hydrolysis with formic acid and just heated the sample, sublimed the sample without treatment by formic acid water?
I personally have not done that experiment, but I believe Daniel Glavin has in the past, not on these meteorites, but has, I assume you're speaking to thermal degradation of the products, and he's determined that that was not an issue.
I'm speaking to the fact that you can get these sort of nucleobases, purines and pyrimidines, by hydrolysis of HCN polymer. And so I'm wondering whether there might be HCN polymer present, and therefore you would get you would need to submit the solid to hydrolysis in order to see those, to break down the HCN polymer.
We have not done those for these meteorites.
Yeah, I don't see Danny or Jason in the room, so I think we're going to have to refer that question. James, why don't you get back to Bob tomorrow? If you're online, Bob, he can send you an email on that to clarify that a little more clearly.
Okay, great.
Yeah.
Thanks.
Okay, Bob. In fact, you have my email address. Why don't you just send me yours? I don't think I have it, but
Will do.
I'll read that. Okay, thanks.
Yeah, I've got to come down there.
Yeah, we really want to see you here, actually.
Okay, great.
Okay, any questions here at Goddard or clarifications?
Where did these meteorites come from? You told me where they were found, but where in space did they come from? What's their origin? From planets? From?
I believe they were most likely asteroids, but I'm not the expert in this.
Okay. No Mars meteorites.
These were not Mars meteorites. I don't think so. I'm fairly sure that they're not Mars meteorites. They would have told me that, I think.
Yeah, I would augment further comment that James made, which is correct. But the outer zone of the asteroid belt is carbon-rich. So these probably came from that outer zone, somewhere between 4 AU and perhaps 4.5 AU, whereas the inner asteroids generally tend to be stonies, occasionally metallic asteroids or meteorites. All right, thanks very much, Jim. Let's go on to Josh Stern. Josh is a student from Brown University, again working with Jason and Danny primarily on derivatization, which is a fancy word he's going to explain, of carboxylic and hydroxylic acids with chiral fluorescent tags, and I won't even attempt to pronounce the name of the tag. So, Josh, go ahead when you're ready.
Okay, so I'm Josh Stern. The title of my talk is Derivatization of some carboxylic and hydroxy acids with the chiral fluorescent tag DBDAPY. Proteins in terrestrial biology are overwhelmingly left-handed, made up of left-handed amino acids. An example, so a left-handed amino acid is an example of a chiral object, like this right-handed desk and this left-handed desk, and that's because the right-handed desk, if you reflect it, you can't superimpose it on its mirror image. An example of an achiral object would be this chair. You reflect that and you can superimpose it on its mirror image. Another example of an achiral object is the molecule of valeric acid. This is superimposable on its mirror image. And then another example of a chiral object is the amino acid isovaline. Reflect that, it will not be superimposable on its mirror image. There's a question of why are the amino acids that we're made of left-handed and not right-handed, and being able to answer this question will help us explain the origin of life. And one clue perhaps is that there's been studies of meteorites and carbonaceous chondrites, and they've found an excess of left-handed isovaline, a significant excess in the meteorites. So we're interested in studying meteorites, and the way we study them is one way to study them is using high-performance liquid chromatography. What you can do is you can take the amino acids in the meteorite and then attach a fluorescent molecule to that acid, to the amino acid, and then put it in the chromatography machine, separate the compound, separate the various amino acids, and then run it through this fluorescence detector. What that'll do is, if you have a high fluorescence measurement, then that is proportional to the amount of amino acid present. And so by this method, you can measure the abundance of each chirality of amino acids and various amino acids. And so the way we derivatize is we tag primary amines. That's the way that we attach this fluorescent tag to it. One thing that I'm not going to focus on very much that I did this summer was I looked at the decay of amino acids that are derivatized with this fluorescent OPA-NAC tag. And this is useful for kind of knowing how long do derivatized amino acids stay around, how viable are they over time at negative 86 degrees Celsius. But what I focused most of my summer on was developing a different way to derivatize carboxylic acids, and which can be applied to amino acids, and using a different fluorescent tag, a different reaction. So what this does is this is a fluorescent, another fluorescent molecule. It's abbreviated RDBDAPY, and you combine that with, in this case, valeric acid. It's got a carboxyl group right here. And this is a non-amino acid. I'll explain that in a minute. The N on the tag bonds to the carbon in this carboxyl group, and the OH goes away, and so you end up with this derivatized valeric acid. This reaction also works if I want to do a hydroxy acid. Hydroxy acid is right here, but it also has this carboxyl group, so you can put that with the DBDAPY, and you'll get a derivatized hydroxy acid. And then it also should work with an amino acid, because the amino acid also has a carboxyl group here, and so the same thing will occur, have a derivatized isovalene. So this would be a really great technique to make happen, because you can study amino acids, hydroxy acids, and carboxylic acids. The reason why we're interested in studying hydroxy acids is, this is kind of busy, but just focus on these two boxes here. This is the Strecker synthesis, and it's thought to be a process that happens on meteorites. And then this is a parallel reaction that occurs that forms the hydroxy acid equivalent of an amino acid. And so that's why we want to study hydroxy acids. It'll help us learn about amino acids. And so this is what my data look like. This bottom graph here is retention time versus fluorescence intensity, and then these three top graphs are retention time versus mass intensity. So each peak corresponds to a distinct compound, and so this peak right here is unreacted DBDAPY. There's a huge excess of it, and we're confident that that really is a DBDAPY because we see the mass peak. We see the mass peak in this window, because you're only counting when it's between this range of 312 to 3.12.4. And then also this is the peak for derivatized valeric acid, and we're confident about that because we see the mass peak at the mass of derivatized valeric acid. And then this is an unknown compound, and we know that the mass is 649. We think that it's a contaminant in our catalysts. So these graphs here are the same as the one before. It's just using a hydroxy acid this time. So here, this peak is DBDAPY, the fluorescent tag, and then I haven't shown that on the mass. But these two small peaks are derivatized hydroxy acid, and we're confident of that because we can see the peak in the mass data. And then this is also an unexplained peak that I don't have time to go into. And so basically, we've had mixed success with these efforts to derivatize carboxylic acids. When you're studying meteorites, you really want to have a very low detection limit because it's a precious sample and because you don't have many amino acids inside the actual meteorite. So we want starting concentration of the acid in this window, 10 to the minus 6, 10 to the minus 10 molar, and this is where I am right now. So there's definitely a long ways to go, and I'm in communication with the author of the original procedure who developed it for use in medicine. And so we have some ideas, and hopefully we'll go somewhere with that. And I'd just like to acknowledge my mentor, Dr. Jason Dworkin, as well as Mr. Jim Doty, who really spent a lot of time teaching me about all the instruments in the lab, and everyone else on the slide. So that's all.
Thank you very much, Josh. That's quite an interesting thing. I must say that it's the first time I've had heard a really clear and concise and understandable explanation of the relation between the mass spectra and the time evolution spectra. It was really quite nice. So let's turn first to our colleagues online and see if we've got any questions out there for you. My, so quiet. All right. Anybody here at Goddard who wishes to ask a question, make a comment? Gee, I think you wowed them all. Okay, thanks very much, Josh.
Okay.
Okay, we're going to now turn to some of the work going on evolved bodies, in particular planets. And as many of you online have heard, the Goddard team is heavily involved in analyses of Mars' atmosphere involving biomarker gases. But today you're going to hear a little bit different spin on that. First, there will be two talks. The first one by Nadia Radova from Connecticut College, who will talk on the spectral analysis of Mars spectra acquired in the 1 to 1.4 micron region. Her mentor is Geronimo Villanueva, who is an NPP postdoc here. Would you take it away?
Thanks. Hi, I'm Nadia Radova, and this summer I worked on analyzing the Martian atmosphere in the 1.1-1.4 micron spectral region. Mars is one of the 4 inner solar system planets, and these planets are characterized with an atmosphere that contains mostly carbon dioxide and nitrogen. In contrast, the Jovian planets contain mostly hydrogen and helium in their atmosphere. However, 2 of the planets from the inner solar system planets, Mars and Earth, contain hydrogen, and thus there is water. Mars is smaller and lighter than the Earth, and that's why the pressure on its surface is very small, 6 to 8 millibars. That's why there is no liquid water found, and water can exist only as vapor or ice, and the water vapor is only 0.03% of the atmosphere. The data I processed was taken with the Keck-2 telescope in Hawaii, and the data was taken along a slit that covers a small region of Mars. There are 3 main filters, NIRSPEC 3, M-wide, and KL, and I processed data from NIRSPEC 3 and M-wide. NIRSPEC 3 is an absorption spectra, that's why you can see gas lines and Fraunhofer or solar lines, while the M-wide filter is radiance spectra, and that's why there are no solar lines. After analyzing the data, I also retrieved the terrestrial lines present in the spectra, due to the fact that Keck-2 is a ground-based telescope. First, in order to process the data, I had to read the image that was taken from Keck-2, where frequency is along the x-axis and latitude is along the y-axis, and the latitude changes with every row. Every order has different frequency, and first I cropped the desired order, and then I had to clean the bad pixels, which are white dots that I had to replace with neighboring black dots. After that, I had to straighten and position horizontally the spectra, because initially the spectra is tilted to one side because of anamorphic optics. After that, I had to match the lines with the model in order to obtain the frequency solution. And finally, I had a transformed and calibrated spectrum that I used in another program to retrieve the topographic view of Mars, where blue is low altitude and red is high altitude. This is the subsolar point, and this is the exact position of where the data was taken. I used the software developed here at the Astrobiology Center at Goddard to obtain the geometrical parameters for every row, to remove telluric and solar lines, and finally to obtain the abundances of gases. This is a graph I obtained after processing every order, and in black you can see the observed spectra, in blue you can see the model, and the difference is plotted here, where every row is a different latitude. And in green you can see known lines. This is a CO2 band, this is a solar line, this is a water line, and in red you can see the model. I processed data from NIRSPEC 3 setting, which is to 1.4 to 1.4 microns, and I found water, carbon dioxide, O2 single delta, and solar lines. After that, I plotted all the data, and in black you can see the observed spectrum, red is the model, and blue is the residual spectrum, which is only real Martian lines and solar lines. Here you can see water lines and the solar line. In order 57, I found CO2 with an isotope 626, solar and water lines. In order 58, I also found CO2 with isotope 626, water and solar lines. And order 60 has O2 lines and solar lines. After that, I processed data from the M-wide setting, which is from 4.6 to 5.4 microns.
and found carbon dioxide, water, carbon oxide, and oxygen lines. And again, I plotted the data. In both orders, I found water and carbon dioxide lines, with the carbon dioxide has an isotope 636. After that, I had to calculate and plot the water vapor column. First, I had to calculate the total air mass, due to the fact that first the solar rays reached the Martian surface, and then the rays reached the Earth. In order to plot the water vapor column, I had to calculate the line area, which depends on the area depends on the water column, the total air mass, and the model line intensity, which is temperature dependent. And the water vapor column is equal to the water abundance, a constant, and the surface pressure. Water on Mars depends on the altitude and also on the season on Mars. On the left, you can see a plot of the water vapor column versus altitude, and you can easily see that the water vapor column in the northern hemisphere is much higher than in the southern. Here you can see the same dependence, where in red I plotted the highest water vapor column, and in purple the lowest water vapor column. The subsolar point is in the northern hemisphere, and that's why it is summer in the northern hemisphere, and water vapor column is highest here. Also, you can see that right here in the southern hemisphere, the water vapor column increases. This is due to the fact that this area is right next to the Hellas Basin, which has a very low altitude. That's why the pressure there is very high, and the water vapor column is high. The same dependence is observed in the northern lowlands due to low altitude. And in the ancient highlands, the altitude is very high, and that's why the pressure is low, and the water vapor column is low. The data I analyzed this summer is going to be used in an infrared survey. And as for future work, I need to analyze unknown features in the spectra, also to process more orders and data sets in order to find the isotopic water ratio and to find the pH of water. And I would like to thank the Astrobiology Center here at Goddard, my mentor Dr. Villanueva, Dr. Muma, Tori, and all interns.
Okay, thank you very much. That's quite interesting. Maybe you could, before we go to the remote sites, maybe you could explain why the blue and red points on that one slide you showed towards the end are different widths. Quite different widths there in that chart.
Yes, it's because of the slit. The slit is not parallel on the left and the right, and the width increases in the north and south parts, and that's why. Is that due to the projection effect of the sphere of the planet? Yeah, so you show it here in latitude, longitude coordinates. It's because of the optics of the telescope, and because Mars is round. Okay, thanks very much. Let's go to our remotes colleagues first and see if there are any questions from the online teams. Okay. Anyone here at Goddard wish to ask a question or make a comment?
What date were these taken?
This is March 22nd, 2003.
Okay, so it would have been late summer in the northern hemisphere.
Yeah.
I guess.
Yeah, I don't know if that came through remotely. Not just did you think so? Okay.
We can hear that.
Okay, good. Thank you. Anyone else? Okay, thanks very much. We look forward to the comparison with the results of the next talk. Okay, very good. Next, we'll hear from Justin Nieusma, who is a student from the College of New Jersey, working this summer under the mentorship of joint mentorship of myself and Geronimo Villanueva on another aspect of the same data set, but emphasizing a different species. Justin, take it away.
Hi, I'm Justin Nieusma from the College of New Jersey. This summer I was working on the analysis of Martian carbon dioxide utilizing high-resolution spectroscopic data. I was working under mostly Dr. Geronimo Villanueva. This is a very similar data set as to what Nadja was working with, or actually the same data set, using from the Keck 2 Observatory, looking at transmittance data. Specifically over here, working from a NIRSPEC 3 filter from 1.1 to 1.4 microns. The orders that I analyzed are the ones in these red boxes, these 5 of them. In this, I found mostly H2O, CO2 was the 2 strongest, as well as a large number of Fraunhofer, also known as solar lines. In particular, I'm going to be focusing on this order right here, order 63, as it has a very strong CO2 presence. First, in looking at CO2, and specifically we're going to be looking at things we can learn about pressure with CO2 for the purpose of this talk, it's very important to look at the geometry of Mars. So here we have a topographic image of the Mars as it was oriented, wherein red is high altitude and correspondingly low pressure, while a blue represents a low altitude and thus a high pressure. So we have our subsolar point is here. This is where the sun is directly overhead. We're about 2 hours from it, so we're looking 2 p.m., and this is where our slit is. It's a very small longitudinal range, but we get a lot of latitude, all the way from the north to south covered, such that if we just left our slit positioned there and let Mars rotate under it over one Martian day, we could map out the entire planet like this. So we're going to be looking at, in this slit, the CO2, how much we have, and corresponding that to pressure. And we should potentially see an increase in pressure in the lowlands, where there's a lower altitude, higher pressure, and also near the Hellas Basin, as there should be a higher pressure there. Now, first, I have to take the data and process it. It starts off very slanted, and it really is meaningless at this point. So after cropping it and cleaning, we want to make it a straight image like this, such that we can say the rows, our y-axis, represents the latitude, and on our x-axis we have frequency. We can actually say that this line here corresponds to this frequency, and so on. Down here we actually have a image representation of a spectral solution, wherein different colors represent different latitudes. So since all of the colors and lines are very close, this is a good straightening solution. If there was a large spread and you'd see different colors all over the place, that means it's not very straight. From there we have to analyze the data. Our white up on top here is the actual data from the order we're looking at, and the blue is a telluric model, or an Earth model that was generated, which using such as the precipitable water and solar factors, we create a theoretical model and we subtract that from our data. So now all we have left is the residuals, which is our Mars component and the Fraunhofer lines. Now we generate this on the bottom. This is retrieval. The red is a retrieval on the theoretical lines that should be in our range. Here we're looking at from 8,200 to 8,320 wave numbers, and we have the strongest lines are all CO2. So all of these red lines you see are CO2. And up here is our data again, and after we removed fringing and a bunch of other effects, and then we look and we see if we can, the lines that should theoretically be there, we match them up to our real lines, and we put these green marks to indicate all the lines that are actually there. Also, we mark off, this is a solar line, there's a line here, but there's no red. We also mark off whole areas in cases where there's so many lines that trying to mark individual ones is not very realistic. And this gives us practically a now fingerprint of our Martian gases. We can look at this, we see what lines are there, and how strong these lines are, and we can learn a lot about what we're looking at, such as in this case we're looking at CO2 626. For those not familiar with that terminology, that means oxygen 16, carbon 12, oxygen 16. And also we can look at, down here we have some information about the CO2 bands that are in this order. Next, formatting the data to make it a little bit more readable and to designate, so you can tell, we have our CO2 lines for different orders. This, once again, this is the order 63, what we were looking at before, and now you can see these are our CO2 lines versus these are the solar lines. And these two orders, the solar lines were very strong, such that we only really can see what we at least believe to be solar lines, although in checking this against Solar Atlas, some of these lines are unknown. So this is not a total useless data per se, because while we don't see the gases we're looking for, we have unknowns here, whether they weren't in the atlas, there was a hole in the atlas or something, so this can later be looked at. Now, as for why I'm looking at CO2, well, CO2 makes up the majority of the Martian atmosphere. Its abundance is more than 95%. So, as such, it demonstrates major atmospheric properties, such as surface pressure and atmospheric temperature, and even can represent the general circulation of the atmosphere. We can see, like by looking at where the CO2 is, where it's going, we can learn a lot about what's going on Mars. Now here I have, this is the image of Mars nearby the slit. Here's the Hellas Basin. And the slit, once again, it takes on this curved appearance due to the projection of our rectangular slit onto a spherical surface, which is now being made into a flat image. So it kind of curves and distorts a little bit, and we get more area in the north and south than near the equator. But what we have is, this is mapping out the pressure. We took from the 8,200 to 8,320 wave number range and summed up all of the CO2 lines we had there and a few calculations involving air mass and everything, and now we have the absolute surface pressure in millibars, going from 6 millibars where it's blue up to 10 millibars here where it's red. Now we have it graphically and color here, and if we take a look, we see more pressure up in the north and the south, which matches our predictions due to the lower altitude, and we see an increase. We have this position right here is higher than the surrounding ones of the pressure, and we have a peak due to its proximity to Hellas Basin, once again fitting our predictions. So the data matches well with what we'd expect by topography, so we can feel fairly certain that this data is correct and we're looking at good results. So some quick conclusions. The data was calibrated with very high precision. We have a high signal-to-noise ratio by studying and removing many instrumental effects such as spectral fringe and electronic ground offsets. The absolute atmospheric surface pressure was retrieved with high confidence and follows sample topographic features. We found what we expected. Many molecular features were identified, though some are still unknown and could be related to biosignatures. We have a lot of the solar lines were identified, but some of them we aren't sure. They could be solar lines. They could be another gas that we weren't looking for. And the data presented here will be part of a comprehensive infrared survey of the Martian spectrum. And these are just some acknowledgments. Thank you.
Okay, first let's go to the remote colleagues, see if anyone out there has a question for you. Carnegie, Ames, Boulder, wherever. Okay, nobody's shouting. Anyone here wish to make a comment?
A question about the solar atlas. Which one did you use?
The solar atlas, I'm not going to remember the exact name. I believe it was by Wallace is one of the names that's coming to mind. I could actually show it to you since you're right here on site. I actually have the book right next to it.
One taken at Kid Peak?
Yeah, it's a Kid Peak.
Yeah, so that has blanks in it.
Yeah, there are certain blanks in some areas. In other spots, we actually had lines where they just had a flat. So.
Right. Where there's high atmospheric absorption, you don't know.
Yeah.
Okay.
I guess the Atmos spectra that you looked at doesn't go down that far in wavelengths, is that right?
Yes.
That cuts off at 2.5 microns, I think.
It would be nice if the Atmos went all the way down there.
It really would.
Yeah.
Mike DeSantis.
Yeah, I just have a general comment. It's interesting to point out that both the water from Nadia's talk and the CO2 follow both the topographic and the latitudinal variation overall. An interesting comparison, of course, is the degree to which the asymmetry compares in each, and that's part of the study, of course.
Mm-hmm.
You don't have a backup slide with that, do you?
No, we did not have time to compare such as mixing ratios and such just yet.
Right.
Well, I thought I noticed that Nadia's water was still increasing towards the North Pole, whereas your CO2 is turning over.
Yeah, that's
and this might suggest an enhancement of water vapor in the extreme north at this season.
Which is late summer, right?
Right. That would be late summer. And it's like today, it's very humid in late summer, whereas the other side would be late winter.
So tune in tomorrow at this time. We'll show you that. Let me ask you a ringer here. In your CO2 spectra, you had a nice picket fence of lines progressing to the right, but let's just have a quick look at that again. No, not that one. That's too crowded. That one, right there. Nice picket fence going off to the right there, but to the left, there's some big bright thing on the left. What is that there? That thing right there. What is that?
That is a band head. I didn't go too much in depth onto the bands, but we have right here, for example, this is one CO2 band, or well, actually it keeps going, but these are the lines that I identified from the band. It is a sigma-sigma, so we don't have a Q, but it's centered right here. Over here is our P branch, and over here is our R branch. And with the R branch, as it progresses, compacts, and it gets closer and closer to lines, and then eventually they turn back on themselves. And this bandhead, it's a large number of lines, kind of all grouped together, and it creates one big, strong CO2 line.
Very good. Very good. Thank you very much. Okay, let's move on to discussions on lunar, on some work that is being done by Heidi Owens from Auburn University on aspects related to future work on the science surface analysis lab on Mars. Heidi? Well, I should say her mentor was Jen Eigenbrode, who was, by the way, actually an astrobiology postdoc at Carnegie for 2 years after getting her PhD at Penn State. So she's an alumna of the NAI for at least the past 7 years, and is now here permanently as a staff member.
All right, like you said, my name is Heidi Owens, and I go to Auburn University in Alabama. I worked with Jen Eigenbrode and the rest of the SAM team on the organic analysis of Mars analog samples and instrument calibration for a field test in Svalbard for SAM. And for those of you that don't know, SAM stands for the Sample Analysis at Mars. It's going to be going on the Mars Science Lab in 2009. Some background. AMACE stands for the Arctic Mars Analog Svalbard Expedition, and the basic idea is to analyze and collect soil samples that live in a remote environment. And you can see Svalbard in the picture. It's north of Norway in the Arctic Circle, so it's extremely cold and extremely remote. And they wanted to bring back some samples and see if our field and our lab instruments can detect any organics in the rocks that we brought back. So I've been working with the GCMS, which stands for Gas Chromatograph and Mass Spectrometer, and it separates compounds based on structure and molecular weight. And a good analogy for this would be balls being blown down a ramp. For example, if you have a ping pong ball, a bowling ball, and a football, the ping pong ball is going to be the most simple and the lightest weight, so it will reach the end first. It's similar, if you apply that to a gas chromatograph, as it's going through a column, the lighter and simpler compounds are going to go through faster and quicker and hit the detector first. So the first thing you see on a chromatogram, which is what you get from a GCMS, the light compounds are going to arrive first, and the heavier, more complex ones are going to arrive later. In each of these, peaks represents a different compound, and on the x-axis you can see the retention time in minutes. So yeah, each of these peaks represents a different compound, and if you analyze one of these peaks, if we chose that one, each one would produce its own mass spectra, which looks like this. On the x-axis you have the mass-to-charge ratio, or the molecular weight, and they have its own unique signature for each compound, and you can identify which compound it is based on how it looks or which numbers you see, and just analyzing that using libraries. So I've been working with an instrument called the Griffin this summer. It's a field instrument, and it's very convenient for field use. It's around 80 pounds. It's less than a 2-foot cube. The problem with it being a field instrument is that it's less sensitive, so it doesn't, produce as many results as a lab instrument. It's also an ion trap mass spectrometer, which is it's different because there's a bunch of ions that are running around loose inside the instrument, so it will attach itself to the compounds as they're fragmenting and going through the column. So it gives slightly different results in the data than a quadruple mass spectrometer, which is what most of our lab instruments are, and also the instrument that they're planning on sending to Mars in 2009. So because of these differences, our libraries do not match up. So if I try and match my data that I got from the Griffin with the national NIST library, then it's going to be different. So my project was wanting to create an internal library using some known standards by running these standards on the Griffin, identifying these compounds, and creating this library. And that way they could take this library to Svalbard, because they're going back this summer, or the fall, and they're going to use this library to compare their samples that they run there based on what I've done. We also wanted to compare the field instrument, the Griffin, to the lab instrument, the Finnegan, and find patterns on how they differ, so they can compare that when they bring it back and run those samples in the fall. And I also wanted to analyze data and results from a natural sample that they brought back from Svalbard last year. So here's a snapshot of the library I created. You can see that there's a chemical name. I know it's kind of small.
formula, molecular weight, and each entry has its own spectra. And these are a list of the standards I've run in a few of the samples, so you can read those. And the library is pretty helpful. If you have your chromatogram and you don't know what is in it, you pick a peak that you want to analyze, which is displayed here, and this is its own chromatogram, or its own mass spectra. And you can match it to the library that we've created, and in this case it's 95% sure that it's decane, and decane spectra is right here. So you can kind of visually see it and match it up as well as with the library itself. So diesel dolomite is a sample that they brought back from Svalbard last year, and it was kind of interesting because dolomite is, when it's formed, it doesn't usually contain organics or anything of that kind. So when they smelled diesel is an indication that there's organics in the rock. So it was kind of interesting, and it caught their attention. And what's interesting on this is, as they ran it through the Griffin, you can see that there's big peaks here, which are very patterned. They're spaced pretty evenly. So you can kind of see this might be an indication that there's some kind of something going on there. And when I analyzed it, I saw that all of the big peaks are alkanes or hydrocarbon chains, which, you know, is kind of weird because you don't usually find organics in a dolomite sample. So the red numbers indicate the masses, the molecular weights. So as you can see, the general trend is that it's going up, which would indicate, you know, which also helps to include, or helps to satisfy the conclusion that they're, what am I trying to say? That they're getting more complex as they go through. So the sample was also run on the Finnegan, which is the lab instrument, and it looks slightly different than the Griffin sample, mainly because there's a lot more peaks that are smaller down. If you zoom in, you'll see a lot of the same things. And once I analyzed those, I saw a lot more aromatics and PAHs than the hydrocarbons, so I thought that was kind of interesting. And again, the molecular weights are listed there. So the comparison of the Griffin and the Finnegan, this is just one sample from the diesel dolomite that we found. The 92 is a junk peak on the Griffin, so you can kind of ignore that. But you can see here that there's a 140 and a 139 and a 169 and a 168 for the masses. And this is, you know, because of the Griffin is an ion trap mass spectrometer, so you're going to see one more than the Finnegan in all the results. And that was pretty typical. So that's just one comparison. So overall conclusions and why it's important for astrobiology. We did find out that the internal library that I created does work. We were able to identify compounds in natural samples. And what really caught the attention of all the scientists is that organics were detected in a rock that's not typically known for being organic rich. So they're going back to Svalbard this year and doing some more analyses and figuring out where these organics originated, if they're modern or ancient, and whether they come from biotic or abiotic sources. So I'd just like to thank NASA Goddard and the Goddard Center for Astrobiology and my mentor and a lot of other people I worked with. So, thank you.
Before we go to the remote sites, let me quickly ask, I noticed that in, I think it was the Griffin mass spec, you had 3 peaks, elution peaks at mass 254. That one?
Yes.
2 mass peaks at 254.
Right.
And presumably they're isomers of the same.
Right, they're just different structures. Mainly, like here you can see the 2-methylheptadecane and 7-methylheptadecane. That just means that methyl group is at a different spot in the structure. Right. So that's why it's eluting at different times.
But the octadecane is really not one of the methyl. It's a straight different. Right. It's just straight. Each structure is going to be different in how it comes out, and it just depends on, you know, whether it's shorter or longer. But then I did notice the same mass peak in the next spectrum, 254. And you didn't cover that range.
Well, I didn't have a chance to analyze every single one of these little peaks. I just, you know, got the big ones for the main part. But if I go back, I'm sure I can find the octadecane.
Why would the amplitudes be so different between the two?
Well, the difference, we ran them at slightly different temperatures. The Griffin, I think, was at 900 degrees Celsius, and the Finnegan was at 1100 degrees Celsius, and the aromatics and the pHs come off at a higher temperature than the alkanes. So there might be more of abundance in the aromatics in the Finnegan. So they're probably still in there, just not as abundant.
Could you actually smell the organics in as well?
Yes, you can. Yeah.
Okay, let's go to the remote sites. Ask if anyone out there has questions for Heidi. Quiet again. Okay, how about locally? Anybody here at Goddard? Good. You've answered the questions perfectly. Anticipated them all, except for mine. All right, thanks. Next, we're going to actually turn to a bit about the lunar record, which is actually critical for understanding early Earth, as some of you appreciate. Lorne Loudin is working with Richard Walker, professor in geosciences at the University of Maryland, who was a co-I and mentor, co-I on our team and a mentor for this program, and with Igor Puftel, who's also in the same group at UM. And they'll talk, Lorne's going to tell us about some of his work on lunar impact melts in 76055.
Thank you, Dr. Nina. Hi, my name is Lorne Loudin. I go to Keene State College in New Hampshire, and my project was fingerprinting late accretion, a study of the lunar impact melt 76055. In the background there you see a picture of the Serenitatis Basin, which was the sample site for the Apollo 17 missions. And what we're concerned about is the composition of the impacting objects that were involved in late accretion, particularly those from the late heavy bombardment, which occurred about 3.9 billion years before present. It has been suggested that the late heavy bombardment delivered prebiotic organics and water to the Earth, and there is still much controversy over what type of objects were bombarding us, whether or not they were asteroids, comets, or both. We look at lunar impact melt breccias because they are the only objects in the solar system which record discrete impacting events. We also like to look at them because the record of impacts on the Moon is much more preserved than it is on Earth because there is no plate tectonics or weathering, so they have a better record of what the bombardment history was during the late heavy bombardment. We looked at highly siderophile elements in 3 200 milligram subsamples of breccia 76055. We looked at isotopic abundance and ratios of rhenium, osmium, iridium, ruthenium, platinum, and palladium. We did the analysis by doing a high pressure temperature digestion, and then we followed by osmium extraction and then anion exchange chemistry to free up the remaining highly siderophile elements. The osmium extracts were analyzed on thermal ionization mass spectrometers, and the remaining highly siderophiles were done by inductively coupled plasma mass spectrometries. Here are some results. This is a graph that shows iridium versus the other highly siderophile elements. These graphs are a good representation of two-component mixing, in this case mixing between an impacting object and the lunar crust. Iridium is believed to be in extremely low abundance in the lunar crust, so it makes a good denominator to plot the other highly siderophile elements against. The two most important things about these graphs are the slopes of the regression lines represent the ratio of the highly siderophile elements, say platinum, to iridium in the impacting object. The y-intercepts over here represent the amount of highly siderophile abundance in the lunar component. What's interesting here also is the enrichment of palladium, platinum, and ruthenium to osmium and rhenium, which almost have zero intercepts, which is interesting from a geological standpoint. Here we have a graph of 187 osmium over 188 osmium versus platinum and iridium. These are the known data for chondrites, the carbonaceous ordinary and enstatite, and the 187 osmium to 188 osmium ratios in the Apollo samples represent the 187 rhenium to 188 osmium ratios in the impacting objects. The x-error bars in this graph represent the range of osmium ratio in the impacting object, and the y-axis bars represent the 2 sigma error for the regression line. As you can see here, the 76055 sample plots within the range of ordinary and enstatite chondrites, and it also overlaps the data for 73215 and 255, which is another breccia from the Apollo 17 sample, or site. I'd also like to point out up here that this is an Apollo 14 sample and 2 other Apollo 17 samples that diverge pretty far from the known chondritic values of highly siderophile element data. Here's a plot of ruthenium over iridium versus platinum and iridium. Again, the 76055 sample plots within the range of some of the primitive chondrites. It also overlaps again with the breccia 73215 and 255. The overlapping with breccias 73215 and 255 leads us to believe that there is incorporation of the same impacting object or 2 different impacting objects with very similar compositions, which is possible. Again, these samples up here, the Apollo 14 and the 2 remaining Apollo 17 samples, diverge from the known chondritic values, which is a very interesting find. We also brought a 200 milligram subsample of the Apollo 17 breccia to the Astrobiology Analytical Lab here at Goddard Space Flight Center to be analyzed for complex organics under the supervision of Dr. Danny Glavin. We did the analysis following his extraction procedures in his 2006 paper. What we found was that the most abundant amine was EACA, which is a nylon contaminant possibly from the sample bags at Johnson Space Flight Center. The second most abundant amine was glycine, and that could either be terrestrial contamination or from the acid hydrolysis of HCN. Another thing to point out is the DL ratios on the right-hand column, which were higher than expected if the source was terrestrial contamination, but they are not inconsistent with bacterially degraded organics. That was all according to Danny Glavin. In conclusion, breccia 76055 is most similar to ordinary and enstatite chondrites on the plots of 187 osmium to 188 osmium versus platinum and iridium, but it also overlaps, as you guys saw in the other graph, with some of the carbonaceous chondrites. It overlaps with the highly siderophile element data for the aphenite samples, so we can conclude that some of the impactors, there's more than one impactor involved, or in conclusion of the same impacting object within the melts. Some impact melts have highly siderophile element signatures which diverge from known chondritic values. The organic analysis only yielded minute trace levels of amino acids, and no non-protein amino acids of extraterrestrial origin were identified. And I'd just like to thank everybody here at Goddard for helping this work go on, and the Isotope Geochemistry Laboratory at the University of Maryland.
So I gather this is, you've got a mixing line for your isotopic, your elemental ratios in several of these. So this, for example, right there.
Yes.
It sure looks like a mixing line. Is that what you're saying?
Well, it could, yeah, but I also found out that since we use iridium for both of the denominators, that might not necessarily be true. As far as this can be interpreted, I'm not too sure on exactly what, I mean, I don't know if it necessarily represents two-component mixing like it did in the other graph. I mean, I think the important, because iridium, again, is the denominator on both sides of the axis, so that might have something to do with that. But there definitely does look to be a trend between the Apollo samples and NWA 4A2 and the primitive chondrites. So.
Okay, let's turn to the colleagues online and see if we've got any questions outside. Anybody from Boulder or Ames? Okay. Inside Goddard, anyone here wish to ask a question or make a comment? No? Well, I had a question, another one, on the amino acids. Could you flip to that slide again? Yeah, stop, go back. I thought the glutamic had an unusual, oh, it's D to L, not L to D, I see. So it's mainly L-type glutamic. Because it was on the L line, and I thought that meant you were seeing an excess of D, and that was quite surprising. It's not what you're saying. Okay. Thanks very much.
Thank you.
All right. And then finally, to go beyond our solar system to the new frontier of exoplanets, Kamen Todorov from Connecticut College, who is working here with his mentor, Drake Deming, will address the question of measuring the temperature of an exoplanet using data from, I believe, Spitzer.
My name is Kamen Todorov. I'm from Connecticut College, and yes, my mentor is Dr. Deming. My project was to try to measure the temperature of an extrasolar planet, transiting extrasolar planet. We're interested in transiting extrasolar planets because they offer us the rare opportunity to see the planet go in front of its own star, which gives us the opportunity to measure and to calculate many more features of the planet, not only a mass and distance from the planet, from the star. The first extrasolar planet, and the one I looked at, is HD 209458b. It was discovered in 1999 by David Sherburne and his team. It's a little bigger than Jupiter, but it's a little less massive, and it's really close to the star, and the period is about 3.5 days. The part of the orbit that I was mostly interested was the secondary transit, and this is when the planet actually goes behind the star. Then we can detect a small infrared drop of brightness, which is due to the fact that we don't see the light coming from the star anymore. The planet is the brightest in the infrared, and therefore we looked at the infrared region because there the drop of brightness will be deepest. And then we just made about 900 images of the star over time, and then we plotted the brightness of the star over time, hoping to see the eclipse. We used the IRS Blue Pickup array on Spitzer Space Telescope. It's centered on the 16 microns, so it's infrared. And then we counted the photons coming from the star. We used aperture photometry, so we just integrated a 5x5 pixel box centered on the star. This 5x5 pixel box also includes the background radiation, and then therefore we had to estimate the background radiation. So for all the 900 images, we made a plot of the pixel value of all of every pixel in the image versus the number of pixels that have that value, and then we fitted a Gaussian, and we can see that the most pixels would have a certain value, and this is our best estimate for the background. Then we subtracted the background from the aperture, from the signal, and we plotted versus time. This is time in days. It's actually Julian date minus a big number, and this is relative intensity, and we see this strange pattern which we call a ramp. We believe this is instrumental effect. We think this is due to electron traps in the individual pixels on the Spitzer CCD. So we corrected that by fitting a baseline, which we subtracted, and we were able to see that. These are all the 900 points, and you can definitely see the eclipse. The eclipse depth is about 0.24%, and the x-axis is just phase of the eclipse. This is a little clearer plot of the same thing. Here, every dot represents an average of 10 neighboring points from the previous plot, so it's a little clearer to see. Then you can actually see the error bars. This eclipse depth corresponds to about 1100 degrees Kelvin for the planet at 16 microns. And obviously this is too hot for liquid water, but the same technique is very interesting because you can actually apply it to Earth-sized transiting exoplanets which are not yet discovered, but hopefully in future they will be. And of course, then the infrared drop of brightness at the secondary eclipse will be a lot smaller. Therefore, we need a bigger IR telescope, for instance, James Webb Space Telescope. Thank you.
Okay, we'll give our chances. First chance to our colleagues online as before. Anyone out there wish to make a comment or ask a question? Okay, anybody here? Goddard? I was actually quite intrigued by this. I mean, where do you think we'll get this larger infrared telescope?
Well, best would be in space because the atmosphere is not. It's quite absorbent in the IR. So there is a project for the James Webb Space Telescope, which we should hopefully be able to do that.
Now, could you go back 2 slides? I think it was that one right there.
Okay.
You know, when I look at this, I almost see structure within the minimum area. So the peak right on the left there. Yeah, exactly. Double root structure.
These two. We're not entirely sure what are these yet. That's something we should look into in the future.
I mean, an imprudent person might even symmetrize the data about the midpoint, bin them, and then write a paper about it. In which case you would get root 2 improvement in the signal noise on that little hump.
Right, but we think this is an instrumental effect, but we don't know what is the reason for that, so we're not ready to do that yet.
And what effect might it have on the derivation of your temperature?
I'm not sure if there would be significant effect, although my biggest error is actually in fitting the baseline. But these two remain whatever baseline I fit. So I'm pretty sure that the impact on the depth wouldn't be that significant.
Okay, thanks very much.
What is the surface temperature of the star?
It's about 5,000 Kelvin.
5,000 Kelvin.
Any other questions or comments? Very good. That concludes the formal talks, and I'd like to offer a round of applause, and I have one more comment. Aside from all of the mentors, most of whom are here today, I'm sure the interns are particularly grateful to one other person in this room who is sitting here modestly smiling, and I'm referring to Corey Eby, and if you pan over to the right there, Corey.
No,
you have a
that's
picture
okay.
of Corey.
Don't worry
Hey, Corey. I don't think it's too much to say that without Corey's attentive help, this would not have been nearly the success that it was this summer and on. We look forward to many summers to come. Thanks very much. So, that's it for today. Thanks very much for coming, people. And please feel free to send messages to the students if